In mathematics, an ellipse is a curve on a plane that surrounds two focal points such that the sum of the distances to the two focal points is constant for every point on the curve. As such, it is a generalization of a circle, which is a special type of an ellipse that has both focal points at the same location. The shape of an ellipse is represented by its eccentricity, which for an ellipse can be any number from 0 to arbitrarily close to but less than 1. Ellipses are the closed type of conic section, a plane curve that results from the intersection of a cone by a plane. Ellipses have many similarities with the other two forms of conic sections, the parabolas and the hyperbolas, both of which are open and unbounded. The cross-section of a cylinder is an ellipse, unless the section is parallel to the axis of the cylinder. Analytically, an ellipse can also be defined as the set of points such that the ratio of the distance of each point on the curve from a given point to the distance from that same point on the curve to a given line is a constant, called the eccentricity of the ellipse. Ellipses are common in physics, astronomy and engineering. For example, the orbit of each planet in the Solar System is approximately an ellipse with the barycenter of the planet-Sun pair at one of the focal points. The same is true for moons orbiting planets and all other systems having two astronomical bodies. The shape of planets and stars are often well described by ellipsoids. Ellipses also arise as images of a circle under parallel projection and the bounded cases of perspective projection, which are simply intersections of the projective cone with the plane of projection. It is also the simplest Lissajous figure, formed when the horizontal and vertical motions are sinusoids with the same frequency. A similar effect leads to elliptical polarization of light in optics. The name lambda lambda epsilon iota psi iota sigma was given by Apollonius of Perga in his Conics, emphasizing the connection of the curve with application of areas. Elements of an ellipse. Ellipses have two perpendicular axes about which the ellipse is symmetric. These axes intersect at the center of the ellipse due to this symmetry. The larger of these two axes, which corresponds to the largest distance between antipodal points on the ellipse, is called the major axis. The smaller of these two axes, and the smallest distance across the ellipse, is called the minor axis. The semi-major axis and the semi-minor axis are one half of the major and minor axes, respectively. These are sometimes called the major and minor semi-axes, the major and minor semi-axes, or major radius and minor radius. The 4 points where these axes cross the ellipse are the vertices and are marked as A, B, and -B. In addition to being at the largest and smallest distance from the center, these points are where the curvature of the ellipse is maximum and minimum. The two foci of an ellipse are two special points F1 and F2 on the ellipse's major axis that are equidistant from the center point. The sum of the distances from any point P on the ellipse to those two foci is constant and equal to the major axis. The distance to the focal point from the center of the ellipse is sometimes called the linear eccentricity, f, of the ellipse. Here it is denoted by f, but it is often denoted by c, due to the Pythagorean theorem and the definition of the ellipse explained in the previous paragraph. F2 equals A2 minus B2. A second equivalent method of constructing an ellipse using a directrix is shown on the plot as the three blue lines. The dashed blue line is the directrix of the ellipse shown. The eccentricity of an ellipse, usually denoted by epsilon or e, is the ratio of the distance between the two foci to the length of the major axis, or e equals 2f, 2a equals f, a. For an ellipse, the eccentricity is between 0 and 1. When the eccentricity is 0, the foci coincide with the center point in the figure as a circle. As the eccentricity tends toward 1, the ellipse gets a more elongated shape. It tends towards a line segment if the two foci remain a finite distance apart, and a parabola if one focus is kept fixed as the other is allowed to move arbitrarily far away. The eccentricity is also equal to the ratio of the distance line PF2 from any particular point on an ellipse to one of the foci to the perpendicular distance to the directrix from the same point. E equals PF2 PD. Drawing ellipses. Pins and string method. The characterization of an ellipse as the locus of points so that sum of the distances to the foci is constant leads to a method of drawing one using two drawing pins, a length of string, and a pencil. In this method, pins are pushed into the paper at 2 points, which become the ellipse's foci. A string tied at each end to the 2 pins and the tip of a pen pulls the loop taut to form a triangle. The tip of the pen then traces an ellipse if it is moved while keeping the string taut. Using 2 pegs and a rope, gardeners use this procedure to outline an elliptical flower bed, thus it is called the gardener's ellipse. Trammell method. An ellipse can also be drawn using a ruler, a set square, and a pencil. Draw 2 perpendicular lines M, N on the paper. These are the major and minor axes of the ellipse. Mark 3 points A, B, C on the ruler, A to C being the length of the semi-major axis and B to C the length of the semi-minor axis. With one hand, move the ruler on the paper, turning and sliding it so as to keep point A always on line N, and B on line M. With the other hand, keep the pencil's tip on the paper, following point C of the ruler. The tip traces out an ellipse. The Trommel of Archimedes, or ellipsograph, is a mechanical device that implements this principle. The ruler is replaced by a rod with a pencil holder at one end, and 2 adjustable side pins that slide into 2 perpendicular slots cut into a metal plate. The mechanism can be used with a router to cut ellipses from board material. The mechanism is also used in a toy called the nothing grinder. Parallelogram method. In the parallelogram method, an ellipse is constructed point by point using equally spaced points on 2 horizontal lines and equally spaced points on 2 vertical lines. It is based on Steiner's theorem on the generation of conic sections. Similar methods exist for the parabola and hyperbola.